One is organized counting with Venn diagrams. So let's go over a couple definitions first. Elements are elements in a set. So an example of an element are the numbers in a set of numbers from 1 to 5. So basically, we're going to list every single element. So the numbers from 1 to 5 are 1, 2, 3, 4, and 5. And another definition is common elements. This is when items in two different sets in a Venn diagram overlap. So if we have a Venn diagram with two circles, aka two sets, is everything right here in the middle, because these elements right here in the middle, where the red is, are in both sets A and set B. Okay, and a Venn diagram, how we're going to draw that always is we're going to draw a box, and we're going to draw either one set in it, two sets, or three sets, all represented by circles. Okay, and like for example, A, B, C. And when we talk about a Venn diagram, and we're going to get more into this, but every single element in all the sets, or even outside of the sets, must be within this box. So this box is like the universal box. It has every single thing in it. Okay, example 1, common elements. So there are 12 students on a soccer team and 16 students on a baseball team, and they go to a tournament. It's like a soccer baseball tournament. So they need to arrange transportation for 20 students. Here's our issue. 16 plus 12 does not equal 20. That must mean that inside this Venn diagram right here, so let's call this S for soccer. It's like the set of students that are on the soccer team, and B is going to be the set of students on the baseball team. Inside this middle right here, there are going to be some students. Okay, so we've kind of already answered B. Okay, explain why you can't just add them. It's called additive counting principle. Okay, so we can just say we cannot add them because 12 plus 16 does not equal 20. So therefore, there are students on both teams. Okay, so we are going to have some number. I'm going to show you this algebraically. Let me get some purple. Okay, and I'm just going to do it on the side, and then I'll keep this box here for the copy. Okay, we're going to have some number, let's call it X. And we know that for soccer, there are going to be 12 students minus however many students are on both teams. And for baseball, there are going to be 16 students minus however many students are on both teams. Again, that intersection right there. So we know that all of these numbers, 12 minus X plus 16 minus X, is all these people are going to add up to 20. There are only going to be 20 elements in this set. Okay, therefore, so this negative X and this X cancel out. We have 12 plus 16, and for that I get 28. So we have 28 minus X equals 20. So we have 28, let's bring this 20 over, so minus 20, because then this X will become positive. So I get X equals 8. So in the middle here, we have 8. Then if we do 12 minus 8, we have 4. And then we do 16 minus 8, and we have 8 again. Okay, so therefore, if we think about it, 4 plus 8, 8 is 16, 17, 18, 19, 20. There are 20 elements in the entire set of students going to this tournament. Okay, so here are some follow-up questions. How many students are on both teams? Okay, so 8. And determine the number of students in the remaining regions of your diagram and explain what those regions represent. Okay, so this region right here, we have 4. right? This is going to be students who play soccer only. Okay, and on the other side, this one here is going to be students who play baseball only. Baseball only. Okay, because we already talked about these 8 students which are in the middle. Okay, and these are students who play on both teams. Students who play on both teams.